Hi, my name is Karam Edis, and in this project I studied Rayleigh-Benard convection in spherical shells. As you all know from our Lab 5, Rayleigh-Benard convection is a form of natural convection, driven by a temperature difference between the bottom and top surfaces. I decided to focus specifically on how this arises in a spherical shell, where the inner surface is heated. Unlike the classic planar case, the curvature of this model introduces interesting effects and asymmetries to the flow behavior. This problem is an important area of study as it closely models geophysical systems such as the Earth's mantle, gas giants, and stars, and more. The model was set up using the non-dimensional, incompressible Navier-Stokes equation, while assuming constant fluid properties to minimize computation time. The simulation domain was a spherical shell with the outer radius defined as 1 and the inner radius set as delta, which will be varied later in the study. A radial gravity field was applied where the gravitational acceleration was proportional to the inverse square of the radius, mimicking a true gravitational force. The inner and outer surfaces were set to a non-dimensional temperature of 1 and 0 respectively. To validate this model, simulations were conducted at a delta value of 0.95. As when delta approaches 1, the model resembles a simple planar case, as the surfaces get very close together. At which point the critical Rayleigh number for the onset of convection is very well documented at 1708. At Rayleigh numbers below this threshold, the system is expected to remain stable with pure conduction, exhibiting a linear vertical temperature profile and a Nusselt number close to 1. As the Rayleigh number exceeds this number, buoyancy-driven convection should initiate, leading to flow patterns and increased heat transfer. The simulations reproduce this behavior very accurately. Below the critical number, the velocity field had a negligible magnitude and resembled simple noise. However, upon increasing the Rayleigh number above this critical value, the model captured the emergence of convective rolls, as shown in the figure to the right, which is plotting a temperature isosurface at a Rayleigh number of 1750. As you can see, it shows the presence of rising columns out of the fluid. The accuracy of the results was analyzed by varying the mesh resolution. The model was tested at 4 different mesh resolutions and compared by computing the Nusselt number and their relative error. The table shows these values, and since the relative error between the normal and fine mesh was under 1%, the normal mesh resolution was chosen for all further simulation, as shown on the right. Now, onto the results. I first performed a parametric study on delta. The figure on the right plots the dimensionless temperature averaged over a spherical surface against the dimensionless radius for different deltas. As delta increases, the model resembles a simple planar case, and the temperature profile becomes more symmetric, with the midpoint approaching 0.5 as we would expect, as you can see on the left. As delta decreases, the asymmetry increases due to the difference in surface areas, with stronger heat fluxes at the inner boundary, as you can see with a sharper gradient on the left side for the lower deltas. This asymmetry implies that heat transfer is dominated by conduction at low delta, while convection remains strong at high delta. Boundary layer models and theories predict that the Nusselt number, which compares the strength of convection to conduction, follows a simple power law relationship with the Rayleigh number, as you can see in the top right there. While this relationship has been validated in planar cases, its applicability to non-planar geometries has been disputed, especially at higher Rayleigh numbers. To investigate this, the model was run at a delta value of 0.6 for Rayleigh numbers ranging from 10 to the 3 to 10 to the 9. And the resulting Nusselt numbers were computed and plotted in the figure to the left along a qubit root fit applied to the data. The close agreement between these two lines suggests that despite the geometric curvature, the simple power law relationship remains effective. To summarize, this study demonstrated how curvature in spherical shells affects natural convection compared to planar systems. It showed that despite the geometry, the classical power law scaling remains a reliable relationship. It also showed that increased curvature leads to greater asymmetry in temperature gradients and thereby more conduction over convection. The model performed well overall, but the assumption of constant properties and uncoupled thermal and fluid systems placed limitations upon the model's accuracy. In future work, I would explore fully coupled dimensional models and turbulence effects as to better understand fluid behavior at high Rayleigh numbers.